So my name is Patrick, and I'm gonna talk to you about the setup of Gerrit that we run at Google. And so maybe a quick poll first: who runs their own Gerrit at home or at their company, or who administrates a Gerrit in one form or the other? Oh, nice. That's like half of the people. Cool. So what I want to really do with you today is take you on a journey, and we take that Gerrit that you all know, and then we'll take it towards the system that we run at Google step by step. And in the end, we hopefully end up with a multi-master and multi-tenant system. And so the first question should be what? What is this person talking about? And that journey will hopefully outline that and take you step by step towards that direction. And so the rest of the talk will be about the setup that we run, and especially about the load balancing system that we recently overhauled at Google. And we had some quite interesting learnings the hard way that we paid for and that you might also be interested in. So multi-tenant, that basically means the ability to serve multiple Gerrit hosts from a single Java process. So basically, you have gerrit-review.googlesource.com and like chromium-review.googlesource.com, and they can technically be served from the same JVM task. Multi-master is the ability to have multiple Gerrit instances like all over the world basically, and you can contact any of them for reads and writes. So most systems have read replicas, and that's more straightforward, and the write replicas is where the juicy meat is. Okay, so we have that one user that is accessing gerrit-review.googlesource.com, and we have that system that is completely open source and that you can download right now and that you can run in hopefully under 10 minutes. That is core Gerrit, and core Gerrit depends on three things mainly, and that is JGit for all the Git stuff. That is multiple indexes like the account index, the group index, and the change index, and that is caches. And all of these three are based on the file system in one way or the other. So I mean, JGit is heavily based on the file system. The index is based on the file system in the end, and some of the caches are in memory, and some of the caches are based on the file system. So now you have a friend, and the friend is wanting to access Go review.googlesource.com. What are you going to do? Well, the first and easy solution is you just start another Gerrit instance, right? And a third one. And you can have all of that in one machine, no problem. You just give them different ports, very easy. And in the end, it's all based on the file system. And all these Gerrit instances, they don't really have to talk to each other. They can just be like separate instances operating on separate ports. And so this is okay-ish, but it's not a real multi-tenant system because it's basically just a creative assembly of Gerrit instances on a single host. And so what you could do is you add another layer on top of that, which is basically a servlet engine that receives all the traffic, checks which host the traffic is for, and then just delegates it into the individual hosts. And to take that one step further, you could make it so that you don't boot up all the Gerrit instances yourself, but rather you have that selection filter doing that for you. So Gerrit has a daemon that runs all of Gerrit, and you could just integrate that into the filter, and when you see, oh, I'm getting a request for Go review, and I don't have that booted up, why not just launch it, instantiate all the objects, and serve the traffic from there? And I mean, so you could do this, and in a similar manner, you can also unload instances when you say, okay, I can load like 5 instances at a time, right? And I'm getting a traffic for the 6th, so in an LOU manner, I'm just unloading one. All right. So with that servlet engine and the selection filter, all of that can happen in a single JVM. Next step, how can Gerrit conquer the world? So let's say you have a master here in the US, and you have that one friend on the West Coast in the US that is gonna like, your Gerrit is so slow, I have no idea, I want to switch to GitHub. And you're like, whoa, I can do better. I know how to do better. So you want to have a new master for this special person on the West Coast. So the key to that is replication, right? And replication comes in two sets, basically. There is objects that you have to replicate, otherwise it's not going to be a multi-master. That is basically all the Git stuff, right? So we talked about this stack before, and JGit is putting objects into disk. And this is the one, or these are the objects that you really have to replicate properly and fast, otherwise your master is falling behind. And the second, so this needs to replicate. And the second layer is stuff that should replicate, and it should replicate fast to like provide a nice user experience, but it really can be best effort. And that is the indices and the caches. That again comes in two layers. So for the caches, if it's fine with you that your master takes like somewhere between 200 and 600 milliseconds more, don't replicate the caches. You can just, you know, have a cold cache in Singapore or in the US and load everything again, no problem. And for the index, it's kind of, it can be best effort, but you should really make an effort to replicate it, right? And so this is also what David talked about with Elasticsearch, is you should have an effort to replicate that index, but it's not a must. And one way is Elasticsearch, but there are also other things. I mean, some of the cloud providers offer index replication, and that could be used, for instance. Okay, so we took that multi-tenant system and replicated it globally. Now it's a multi-tenant and multi-master system, actually pretty close to what we run at Google. So this is the stack that we run in total. We have that selection filters and a couple of other filters to decide what the traffic is for, which host it is going into. And we are also based on JGit, no magic there. We have indexes and caches that replicate. And all of our system is basically based on a file system and on Bigtable. That is nice on its own because that provides some replication mechanism. But if you say there is magic happening, then the magic is probably happening at the Git layer at Google, which does a majority consensus across all the cells. So when you are pushing anything that is Git, or with NodeDB anything that is a review, what would happen is the system tries to achieve a majority in all the cells and write your objects to the majority. And if that is acknowledged, you get a green light on the push, basically. And majority consensus also means that like you only have it in so many cells, right? You don't have it in all the cells. And so some of that replication is happening in the long tail by replication events that eventually get acknowledged by the cell, and so your object is written to all the masters. Our indexes and caches are also replicated, but I have to say that like some of them are just in memory, and so they have an in-memory component, and they have a component that is replicated on top of Bigtable. So redundancy in all the things, yay. We run 5 data centers across 3 continents with exactly the stack we just saw. And that gives us a good latency for most of our users, I would say. Okay, so the second part of the talk is about load balancing. Now we have a system that we devise together that is multi-master, multi-tenant, so every task can serve any request. But just because it can doesn't mean you want it to, right? Because it has in-memory caches, or it's in Singapore and you are in the US, and that's a pretty long line. And so the question is, what do we do if the biggest machine isn't big enough and we want to optimize? And so the idea is that we want to reduce the latency that comes out of cold caches and minimize the site loads. So I've talked a bit in the multi-tenant system about what a site load is, right? So you're serving a request for gerrit@googlesearch.com, and you don't have it in memory, so your filter would actually go to disk and load some of the stuff to be able to serve your request. Now say you have a fleet of 300 such tasks globally, you really want to serve gerrit.review.googlesearch.com from only like 5. Because if you serve it from 300 and you get 300 requests in like a round robin manner, all that would happen is you add that latency to every single request, and then you dump it because you have to serve so many sites. And the second motivation is that you want to distribute the load. I mean, if it would be only about distributing the load, you could just do round robin. Makes perfectly sense, it's perfectly fine. But then you don't have all the benefits that I just talked about. So what do we really want? We want a system that dynamically scales based on changing load patterns and changing load in general. We want a system that can optimize the caches. So we want to send the requests for a specific site or a specific repo to the fewest amount of possible tasks. And basically, it's 2 premises, right? Serve it from one machine as long as it fits on the machine, and serve it from more machines if you have to. Okay, so in the stack at Google, you saw 2 load balancing levels, and we're going to that now. What you see down there in this picture is the Gerrit task, which contains all of the stack that we had like expanded in the previous slide. Let's start top down. We have a user that uses JSON in the browser because they're on PolyGerrit. And the first thing their JSON request is hitting is a level 1 load balancer. What that is doing is it's routing your request by geographic proximity. So we have 5 data centers at Google, and it just picks the one where the latency on the request to be received at the data center is the lowest. When it goes into the data center, we have another load balancer, and this is the one I'll talk about more, because this is the one where some Gerrit specifics happen. The level 1 is more general. And one thing about the level 1 that I'd like to add is that it can do spillover traffic. So per data center, you can say, okay, I can handle like a maximum amount of QPS. And if that is reached, or if we exceed it, then just route the spillover traffic to other data centers. Okay, let's dive into that level 2 load balancer. What you want to do is we want to know how much traffic we get in each Gerrit task. And we want to be able to, in the load balancer, know where a single request should go. And we want to know that fast. So in the setup, we just add 3 things. We add a component to every Gerrit task that provides functionality so that we can actually report the load that we are handling right now. Load can be anything, can be QPS, can be a custom metric. We just want to know, hey, Gerrit task, like what is your current load? We use a system called Slicer that I'll talk about in a second, and it's adding that there. The second component that we're adding is in the load balancer. We actually want to have a query interface, right? We want to know, we have a request for Gerrit review googlesearch.com, where should it go? And that should be served in memory and should just be updated regularly with new assignments in the background so we don't add another component of latency by making remote procedure calls. And then there is this component that's like coordinating everything. It's called an assigner. It takes all the load metrics that we report, generates like new assignments, and gives it to the query interface. We use a system called Slicer. There is a very nice paper I can recommend, published last fall. It's basically a load balancer that works on custom keys that you define, and I'll go into that in a second. And it can do automatic resharding based on new traffic patterns. So if any of your hosts suddenly receives more traffic, it just gets served from more tasks, or it reshards the whole system. And this is a good system for local sharding, so everything that happens within the data center. We do not use it for inter-data center routing, so that is all done by geographic proximity. So the system works on an int64 key, and if you'd write like all int64 numbers as hex down, and then you have to, you get a lot of numbers, right? And you want to have that in a more discrete way, so you just slice that key space into, say, 400 slices. And what that gives you is 400 ranges where the key can be, and you can take any of those ranges and assign it to one or more tasks to serve them. And so you say, the host name is my key, for instance, right? Gerrit.review.googlesearch.com, and you just hash it, and so that it lies in this bounds, and then maybe it's in the first range, and so it is assigned to a single task with an index 0. What can we do if the load changes? So say we have that key for Gerrit, and it lies in the first range, and now the traffic changes. And when the traffic changes, there are basically two options. The option one is we assign more tasks. So we just add task number 6, right? And then it's pretty much round robin between task 0 and task 6. The second option is, we have like in64, but we split it into 400 slices. Why not split it into 600 or 800, right? To get a more, to get a better grip on each of the keys. So we could also do that, and then maybe we factor out the load for Gerrit review and for Go review, and so we can put them on different hosts. We do that for Gerrit, and one of the things we want for Gerrit is when we have to split up per host traffic, we want to have affinity on the repository, so on the project, because there are also caches that are just living on the project. And when, say, android-review.googlesource.com is a very big host, and so we're serving it from a lot of tasks, and we don't want all these tasks to just serve general traffic on Android, but we want to serve a task for Android project 1 from here and Android project 2 from there, so that we optimize like the second layer of caches. And so what we do is we just like hack this key together based on host and project to achieve exactly that. So before load, all of this Chromium key space is served from a single host, and then when load increases, we just split the key space for Chromium into Chromium source and OS metadata. So this is a graph that we were able to get after we've implemented that load balancer. And what it shows is the load that we handle on each of the tasks in one data center is represented by a line in that graph and by a different color. And what you can see is they're all really nicely aligned. So they all serve exactly the same amount of traffic, which is really what you want. Does anybody know, or does anybody have an idea of what's wrong in this picture? Or what can be wrong?
Big spike.
Oh, the big spike, thanks for that. The spike is actually, so here's the weekend. That's a weekend. Nobody's working on the weekend, and that's weekdays, and that's nights.
There was a big spike there, or just went out, they got all the traffic.
Right, that is true. But this is kind of fine because the load balancer needs like minutes to adjust. So this is okay. Any other ideas? Yeah?
Well, I think like you touched on earlier, if the distribution's so even, does that mean you're getting a lot of cache misses?
No, caches are fine. Caches are okay. What if one of the projects is 100 times the size of the others and you're optimizing on queries per second? So the system will just burn really, really hard. And we had that in May when we have the exactly same load balancer for Git traffic. And in May, what happened to us is we saw that graph and we were all like, oh, this is really nice and this is perfect, right? And then people were writing us bugs and emails saying like, are you still serving any traffic or is the system down completely? And so we looked at the graph and said, no, it's like, this is great, right? And so it turned out that like Android has a lot of large repositories, large in terms of the number of references they have, in terms of like the objects they check into Git. And so we were all just optimizing for queries per second. So some of our tasks were just having to do like a lot of like CPU intensive work in order to like serve the traffic, while others, served hosts that were really easygoing, really light, And so some just burned and others were fine. And the way we solved this for Git is we don't need affinity on all the requests, same for Gerrit. And so we excluded them from this per repository affinity because it doesn't optimize anything anyway. And so we worked around this. There is an extra in the system that a nice load balancer can give you, and that is pre-warming caches. So what the load balancer can do for you is saying, oh, traffic is changing. I need to reconsider how I distribute it to the system. And then to each task, it's basically saying, hey, I'm going to give you an assignment of gerritreview.googlesource.com with a notice of 30 seconds. And so that 30 seconds you can use to pre-warm caches, basically. That is especially nice if you restart your tasks, because when a task restarts, like all its caches are gone, right? Complete memory is flushed. And when it comes up, the load balancer says, hey, this is the list of hosts you are going to handle. And you can just take that and pre-warm all of the caches to reduce latency, basically. And so this graph is showing the impact of a cache warmer on our system on the 99 percentile latency, so really on the long tail of request latency. And again, this looks nice, right? It brought the latency down by maybe a third, so 30% roundabout. So my question's again, what's wrong? So what if a task starts dying during peak traffic, and you get the load balancer says, oh, you're gonna handle this, and then 2 seconds later, the load balancer says, oh no, I reconsidered, you're gonna handle this. Again, you're gonna watch your system burn and it's being really on fire because you're serving peak traffic, so you're at 90% CPU anyway, and then that load balancer comes in and reconsiders its assignments like every 2 seconds. And so you're just loading and unloading sites like all the time. We also had that. It was very inconvenient. And the way to work around this in that case is just to make this cache warming really a best effort thing. So you can do it if you're like below 50% CPU, for instance, when you really have like time to do fancy things. And when you're receiving peak traffic, you just only handle peak traffic, no optimizations made. Right. So the question is, how do we do this in a non-Google setup? And there are actually plenty of options. With the new Gerrit release in 2.15, we adapted to a new URL scheme. And that new URL scheme includes the project name in the whole URL. So previously, you would have like gerritreview.google.com/c/a number. And there is no way to directly infer which project this is for. So there's no way to do like exactly that load balancing that we just saw. And what we did in 2.15 is just add the project before that so that the extraction of both host and project can be static. You could do that before, but you would have to do a secondary index lookup, which most open source systems like HAProxy or Nginx don't support. And so this is like step one towards an open source load balancer. And of course, there are many cloud products like Google Cloud Load Balancing and others that you can use to like achieve the same thing, basically. Okay, let's wrap this up. So we were on a journey. We took open source Gerrit, we added site selection, and what we got is multi-tenant Gerrit. And then we took this multi-tenant Gerrit and added replication, and what that gave us is multi-master Gerrit. And then we took that and added load balancing and lots of failures and lots of fixes, and we got pretty much the Gerrit that we have at Google, which brings me to the end of this talk, and I hope you enjoyed it and I have many questions.
Like, how strategic is Gerrit at Google? Do you have other code review systems? And if so, how well used is Gerrit versus the others?
I can answer that partly. So we have another code review system for internal use only. And Gerrit is basically used whenever we're doing open source stuff. So for Go, for Chromium, for Android, for Gerrit itself, basically whenever a Google team wants to collaborate with open source users, or in general with users that are not sitting at Google. Right. Is that answering your question? Kind of, yeah. No stress. I kind of, right.
I can say something more. So Historically, the code base at Google was developed in Perforce, like the search engine and everything around it. And we kind of ported that from Perforce to a home-built system called Piper, which has been published about. And around that system, we have a whole tooling ecosystem, which is internal. Parallel to that, Google started doing lots of projects that had nothing to do with our internal code base for the search engine. And so Android, for example, was developed to be available outside, and so it used Git. And so what we see that a lot of projects inside Google, when they start developing from scratch, they're thinking about, well, what system shall we use? And then many people say, well, we're just going to use Git because that's what we know and we like. And then they want to have code review for Git, and then they end up with us. And so it's actually very popular inside Google.
I would like to ask a question because all this stuff is really cool, but my understanding is that you got two levels of load balancer. The first one decides the location, and the second one decides what you do inside the data center.
Exactly.
What about if a location is completely off? It means that the location has big problems. Maybe it's not completely offline, but some of the nodes are not able to cope with the load. Or you mentioned before that you had you don't wait for the consensus of all the nodes. So maybe you're unlucky and that location had a very low percentage of consensus. And some of the nodes, they don't have really, the location doesn't have really the latest and greatest of that repo. And maybe a location that is not so inconvenient for me may have the repo that I want, but my location doesn't have it. And that happened, I remember, in the Gerrit project as well. So our guys in Europe, they were unlucky. We were getting maybe the location that was screwed up a little bit. And then we were saying, guys, this is not working. And they would say, yeah, but it's all working for us in the US. And actually, the location wasn't down, but was misbehaving, or maybe the data was outdated and so on. How do you solve this problem? How did you solve this problem?
So the problem that you're talking about is basically replication lag, right? So you have the objects in one location, but not in the other. And usually our replication lag is in O of seconds, but it can happen in exactly that case that you described, that like one location is just really slow on getting the objects. And that happens from time to time. And we have metrics that say what the replication lag like as a count of objects that is not in that cell is. And when it exceeds like a threshold, we'd receive a page, or we just like shut that data center off. And when I say shut off, I don't mean shut off, but I mean like cut off the traffic. So the data center would not receive user traffic anymore, but it would still be able to get all the replication done. And like when we decrease the count of objects that we have to replicate, we can just send traffic there again. And that shutting off the traffic is happening at this level 1 load balancer, where we basically say that data center is bad, like don't send anything there.
Okay, in that case, then the traffic goes to another location that maybe is lower, but you start getting the traffic as well.
Exactly. So you add like the 50 to 100 milliseconds to go to another data center, but you have the objects.
And the second question is, inside the task, do all the tasks have exactly the same setup, or do you have a kind of microservice architecture inside by saying some of the tasks that are, let's say, more dedicated to this type of operations, other for another? So for instance, I don't know, serving some kind of basic operation that just happens in memory is one thing, but maybe doing an intraline diff of a change is a different thing. So
the answer is no in general. So all of our tasks are the same. With one exception, we run a service that just checks access control lists on Gerrit, so that when we receive Git traffic on the Git service, we don't have to contact our Gerrit service to check like the access control, but we can really just talk to this one specific service that just knows how to read project configs from Gerrit and how to like tell authoritatively Git yes or no. But apart from that, it's 100% the same in every task, which is also what this stack was suggesting. Any more questions? Cool, thank you very much.